Hi, my name is Ike Nassi. Today I'm going to talk about some of the insights and some of the motivations behind the TidalScale technology. So first, by way of introduction, who exactly is Ike Nassi? Started off as a mathematician, moved into computational theory. I've been a PhD computer scientist for a very, very long time. Some would call me a pioneer. I think of myself as an engineer. I'm an entrepreneur. I've done 4 startups. I have 17 awarded patents, and there's many more pending. I also had an interest in multiprocessors and parallel processing, so I helped start a company called Encore Computer with Gordon Bell. After I demonstrated the DARPA project I was working on to DARPA, I moved to Apple Computer, where eventually I became the senior vice president of software. After that, I built something called an internet phone. It was the original iPhone. In fact, we called it the iPhone. That was in 1997. Eventually wound up as the executive vice president and chief scientist at SAP. But the other thing that I've done that is, I would say, unusual is I've had one foot in academia and one foot in industry my whole career. So I've had research affiliations at Stanford University, University of California at Berkeley, and twice at MIT. Currently, I'm a professor of computer science and engineering at UC Santa Cruz. I'm also a founding trustee at the Computer History Museum. And currently, I am CTO, Chief Technology Officer, founder, and chairman of TidalScale. Let me start off by talking about the TidalScale value proposition. There are 4 elements when I started the company, and those 4 elements of the value proposition are still true today. I'll explain each as we go along, but let me summarize them first. The first thing is to scale. We wanted the customers to be able to easily increase, and in some cases decrease, the size of the computing environment depending on application needs. The second thing is we didn't want customers to have to do a lot of work to use TidalScale. We wanted, in fact, to minimize or eliminate any barriers to make it easy to use TidalScale. The third thing was optimization. We thought that it would be a good idea to have our software self-optimize the workloads completely automatically without any user intervention. And the fourth thing we wanted was not as a point product. We wanted the system to evolve over time and automatically take advantage of increasing hardware performance, because you know hardware is going to increase in performance over time. Virtualization started becoming an important part of the industry because of the software flexibility it allowed. It allowed enterprises to run applications concurrently on multiple operating systems on the same hardware platform at the same time without having to change the applications or operating systems at all. 0 changes. Observing its emerging importance, Intel and others started improving the hardware support for virtualization. Note that early on, there was a misguided, in my opinion, a misguided emphasis on increasing the number of processors and at the same time minimizing the importance of increasing memory capacity. Around 2008, even though SAP was a software company, we observed that memory density was increasing, as well as processor density. And by processor density, I mean the number of processing elements per chip. But the irony was that processor density was growing faster than the amount of memory you could manage per processor. The memory density wasn't keeping up. Memory per processor was actually trending in the wrong direction. In our opinion, enterprise software needed the opposite. It wanted more memory relative to the number of processors, especially when the popularity of big data started to increase. So why is memory important? It's really pretty simple. We're generating a lot more data these days, and where does it get stored? It gets stored in memory. It gets processed out of memory. DRAM is very fast compared to everything else, except perhaps high-speed data caches built directly into processors. But these are very limited in size, relatively speaking. The fact is, there is no alternative to fast DRAM. Let me say that again. There is no alternative to fast DRAM. You might ask about virtual memory. Virtual memory seems to effectively free the programmer from having to deal with the memory capacity issue. Virtual memory makes the programmer's job a lot easier for sure. We can put a lot of data in virtual memory. But there's a problem. Virtual memory must get mapped to physical DRAM before it can be accessed by a processor. Since virtual memory is many times larger than DRAM, the operating system must resort to managing a mapping between virtual memory and physical memory. To do this, the OS implements a concept called paging, in which portions of virtual memory get paged out to slower forms of storage like disks, when the DRAM in which that memory resides must be used for some other purpose. In that case, when that happens, that virtual memory will again be needed later. It must be retrieved back from the disk and placed back into DRAM. This takes a lot of time, increasing overhead. There's no such thing as a free lunch. I mean, even if you have 4 terabytes of physical memory on a server, you might have 256 terabytes of virtual memory in the server. And you got to manage that discrepancy. There's no such thing as a free lunch. What about flash, also called persistent memory? Persistent memory is not the answer. Flash is much faster than disks, for sure. No debate. Unfortunately, it's several orders of magnitude slower than DRAM. Well, what about SSDs? Well, SSDs are made from flash, but are packaged to look to software like traditional disks, and therefore often have the same performance characteristics as flash at best. So SSDs are not the answer. One last time, there's no alternative to fast DRAM. So if you could keep your data in DRAM, you could achieve the fastest access possible. But here's a problem. The capacity of servers to hold DRAM is very limited relative to our ambitions. DRAM is also very expensive, and we usually want far more DRAM than we can afford. At SAP, we worked out an approach called in-memory databases, and we were not alone. Many others did that, like Oracle. It's a great idea. It certainly works. If you could keep the database in memory, database access will run much faster. But in addition to the expense, there's another fundamental flaw. The amount of DRAM one can physically put on a server is limited not by your budget, but how much the processor can physically access. This limitation is determined by the number of address pins, data pins, and control pins you can physically put on a modern processor. The sad truth is that there are physical limits on the number of pins on a processor that prevent you from putting an unlimited amount of DRAM directly attached to a processor. So instead of a hardware approach, there were many efforts to address this problem through software. This resulted in a renewed interest in distributed computing, in which we added memory by adding servers over the network. That's why technologies like Hadoop were invented. But historically, distributed computing solutions require you to write custom applications to access the data on different servers. And one had to figure out in advance how to partition data amongst a set of servers and then maintain that data partitioning. This approach to scaling rarely works for legacy software. TidalScale's solution is fundamentally different and new. We hide the complexity of distributed computing among the servers. We still have multiple servers connected over a network, and that allows us to take full advantage of the economies of scale of modern commodity servers. But we organize these servers very differently. We use a new form of virtualization that allows a single virtual machine to be distributed amongst a set of physical servers. TidalScale allows you to create one virtual machine running across multiple servers. We call this single distributed virtual machine a software-defined server. Now, this is in contrast to what you might think of as a virtual machine, in which you have multiple virtual machines running on a physical server. We have one virtual machine running on multiple physical servers. It combines the low-cost economics of scale-out servers with the simplicity of scale-up. I believe in this so much, I put it on my car. Scale. Consider the problem of adding more processors or memory to a server. It's at best hard and may not even be possible. Unlike a physical server whose configuration is fixed at time of manufacture or time of purchase, we can easily add more memory and more processors to a software-defined server simply by adding one or more physical servers into a cluster. To do this, we put the new server on the same LAN segment as the others, make some minor configuration changes using our Wave Runner software in the front end, and then just reboot. In effect, TidalScale has created a new architectural level in the data center computing hierarchy. The capacity of the software-defined server can be adjusted up or down as determined by workload and is very easily changeable. The management of the physical servers and the mapping between the virtual and physical is all done behind the scenes. TidalScale solution requires no modifications to an operating system like Linux, a database like Oracle or HANA, or any applications. Just like the virtual machines you may be accustomed to, applications can just run with no modifications at all. Can't be any simpler than that, right? In order to allow programs to run efficiently, we actually use the same features of the modern microprocessors that are used in other virtualization systems. I'm going to explain how. Earlier, I mentioned the hardware support for virtualization. Here's one element of TidalScale's secret sauce. Unlike older generations of processors, modern hardware supports not one level of dynamic address translation, but two. The first level of dynamic address translation is managed by the operating system, and the second is managed by TidalScale. A modern operating system manages the first level of page tables. Using these tables that the operating system creates and manages, the hardware translates a virtual address to what the operating system thinks of as a physical address. It does this at hardware speed. Why do I say it thinks of this as a physical address? The resulting address is we call the guest physical address. The operating system thinks of it as a physical address, but it's not. Behind the scenes, the hardware does this again with a second level of page table controlled and managed by TidalScale. This translates the guest physical address into a real physical hardware address, again, done at hardware speed. To operationalize the software-defined server, TidalScale has developed a piece of software called a Distributed HyperKernel. Each server runs a single instance of a hyperkernel. Each instance cooperates with all the others. The distributed hyperkernel is precisely the collection of cooperating, identical hyperkernels, each running on its own physical server. These hyperkernels negotiate amongst themselves to manage all the physical resources an operating system needs without interfering with the operating system in any way. The hyperkernels perform this automatically, dynamically, and adaptively over time. They monitor the various virtual resources like virtual processors and virtual memory without interrupting normal operating system operation. Each hyperkernel manages its own local physical resources. This is not magic. The operating system has a fictionalized view of the hardware it is running on. In fact, it doesn't even know it's fictionalized. It thinks it's real. It's like living in a highly detailed, completely utopian simulation of real life, the kind you might read about in a science fiction novel. How would you know you're living in this very complete, well-defined simulation? You wouldn't. How far can you push the simulation? After all, a virtual processor needs to run on a physical processor to get any work done at all. And that physical processor can only see what is local to it. For example, the virtual processor has been told that all memory is local, and it has no idea that it's really distributed. When reality intercedes and the physical processor running that virtual processor cannot actually find its local memory, how can it do its job? Simple answer is it can't. It generates a fault in the form of an interrupt that gets trapped by the hyperkernel and therefore is invisible to the operating system. The hyperkernel then addresses the problem and returns, and after it addresses the problem, it returns control back to the virtual processor so it can continue. Let's take the simplest possible case. The simplest case is a read access to non-local memory. The hyperkernel might make a request for a copy of the non-local memory and send the request to the node that actually has that memory. When that remote node having that memory receives the request, it can then send the memory back to the requesting node, satisfying the request. Now there are two copies of that memory. Is that a problem? No, it's perfectly okay. Each node accesses that memory at local hardware speed. If it's a memory location being written into, it's a little more complicated. The hyperkernel has to ensure that there are no stale copies of the memory before the write completes. This is also not difficult. In both cases, read and write, the processor and the memory they need become co-located, allowing them to run at machine speed until the next time a non-local request is made, and so on. Suppose you had multiple virtual processors needing the same memory. Well, that's an example where we need a more complicated strategy. Each hyperkernel watches the access patterns and tries to make sure a set of processors that need a set of pages are themselves all co-located. And if they are, things are great. The computation proceeds at machine speed. Another thing to consider is this. Instead of fetching memory, we might choose to migrate the virtual processors to the memory rather than migrate the memory to the processor. This may sound a bit weird, but it's an extremely powerful idea and it's very inexpensive. It turns out that the hardware support for virtualization includes an instruction that takes a snapshot of the state of the processor and puts that state into a block of memory. It typically fits into about 6,400 bytes of memory. We can then transfer that block of memory from one node to another node, and then use a parallel instruction, a second instruction, to restore the snapshot of that processor from the saved state back into the processor at the destination location. You might think this is expensive. I assure you it's not. Think of a couple of instructions, one to save, one to restore, and transferring 6,400 bytes of memory over a 10 gigabit or 25 gigabit Ethernet. We can do these operations millions and billions of times, and no one would notice any performance degradation. After all, consider how inexpensive this is relative to, for example, paging to a disk. It's worth asking how the hyperkernel determines the best strategy, like fetching memory or migrating a processor. Which should I do? The hyperkernel keeps a set of strategic alternatives. Each strategic alternative is represented by a set of equations, one equation per strategic alternative. Each equation consists of a nonlinear weighted polynomial. The polynomials use a combination of factors, examples of which might be recent history of access patterns, the kind of interrupt that occurred, the percentage of time we're spending in the guess versus the hyperkernel, any congestion on the network, and so forth and so on. Each polynomial is evaluated, and we use the result to determine which strategy is likely to be the best. The evaluation of the polynomial is cheap. It's a bunch of multiplies and adds, and at the end we do a comparison. So it's really quite inexpensive. when the chosen strategy executes, the changes are recorded, they're remembered, so that the necessary data is local, so that the node can efficiently evaluate the potential strategies next time around. Suppose the access patterns change over time, like from 1 minute to the next or 1 second to the next. The individual hyperkernels acting in cooperation with one another need to learn on an ongoing basis what the ideal associations are between processors and memory, and adjust the placement of these resources dynamically and adaptively. And this is what we mean when we say we employ dynamic, adaptive, automatic machine learning between the hyperkernel and the hardware. The hyperkernel learns at any given instant in time where to place all these resources. At any given instant in time, processors and memory are migrating among nodes to achieve good performance, step by step through simple machine learning algorithms. Most of the time, the hyperkernel is not running and therefore not using any resources. That means the guest operating system can use the resources. It only wakes up when it has to deal with a fault. The processors are therefore usually running the guest operating system, the database, and the target applications. The system is usually doing the kind of productive work it was intended to do. It probably goes without saying that patterns of future access cannot be precisely predicted. We certainly have no special powers to predict the future, but we can react to situations in microseconds to quickly and automatically optimize local performance without human intervention. What about all the specialized hardware that's needed to run this distributed hyperkernel? There isn't any. It runs on standard Intel processors and uses standard Ethernet. What about new models of processors with increased core counts? No problem. The hyperkernel adapts. What about increasing hyperthreads per core? No problem. The hyperkernel adapts. What about new versions of Linux? No problem. The distributed hyperkernel presents a virtual machine to the operating system that looks precisely like a standard hardware server. If Linux were to have a problem with that, it would have a problem with any of the myriad of standard hardware servers on the market. In fact, we used to run the standard Linux server test acceptance procedures just to make sure that our virtual server looks like a real hardware server. We don't have to do that on a regular basis anymore since we stopped seeing incompatible failures like this years ago. I presented some of the fundamental reasons why TidalScale was created and how it operates to achieve performance and economic goals. It's a very exciting advance in data center architecture, and there is much more to come. We're always working to increase performance and reliability and to make our system extremely easy to use. So just to recap the value proposition: scale, simplify, optimize, evolve.